In the last video of this lecture, we'll take a look at how these principles, sequence-to-sequence models, and in particular recurrent neural networks, can be used in a large and successful model that is often used in production. And for that, we'll look at the ELMo system, a language model. To set the scene, we'll start with one of ELMo's predecessors to place it in context, which is Word2Vec. And Word2Vec is a method that's based on a very, very simple neural network, and it is used to learn representations of words. So imagine to start with that we have a large corpus, a large collection of natural language, and we want to learn representations, vector representations of its words. What we do is we slide a window over the whole text, and at each point in this process, we'll look at the middle word in the window, and we take the words that are next to it, the two words to the left and the two words to the right, to represent its context. And our task is, given a word, predict which words are likely to occur in its context. So sliding this window over our whole corpus, we collect a data set of which words we might see in the data and which words we might see in its context. So for every occurrence of a word, we get 4 context words. And if a word occurs multiple times, then we get lots more context words, 4 every time we see it. And our goal now is to build a neural network that takes the word on the left and predicts which words we might see on the right. So if we have 100,000 words, we set up a very simple neural network like this with 100,000 inputs, much smaller hidden layer, in this case of 300, and then again 100,000 outputs. And note that the hidden layer here is linear. So we're not even learning a nonlinearity, we're just learning this bottleneck of linearly projecting this 100,000 dimensional vector to a 300 dimensional space. And of course these 100, so we have this neural network that is has an input layer that is as wide as the number of words we have. We feed it a one-hot encoding of the word X. It's passed through this linear layer. We get an output of 100,000 dimensions, which we softmax so that we get a probability distribution over all words. And then we can simply train to maximize the log likelihood of the observations that we have on the left. And if we train this and we do so until the loss converges, what we can do is split up the neural network, throw away the second layer, keep only the first layer, and let the values on the hidden layer be our embeddings for the words. So our embedding for the word compare is the 300 values that we get on the hidden layer if we feed it the one-hot vector for compare. And this is a very clear instance of the principle that I discussed in the first video, which is that if you feed a one-hot vector to a neural network, you are usually implicitly training an embedding layer. So here the first thing that happens to our one-hot vector for the word compare is that it's multiplied by a weight matrix. And when we multiply a one-hot vector by a weight matrix, we are essentially just selecting one of its columns. So that column is in essence the embedding vector that we get for the word compare. And what we see when we train this neural network on a large corpus of text is that these embedding vectors very neatly become to represent the relations that we know to exist between words. So for instance, if we look up the embedding vectors after training for king, woman, man, and queen, we see that if we subtract man from woman, we get a kind of direction in space, which is the direction that goes from a male word like man towards a female word like woman. If we add that direction to the word king and see which is the embedding vector that is closest to the point we end up with, that word is queen, or that is the embedding vector of the word queen. And there are a couple of examples like this. It doesn't always work, but it works often enough to suggest that there really is some kind of semantics captured in these word embeddings that are produced in this way. So this gives us very useful word embeddings that we can use for many different settings. Before we move on, there is one word of warning. The word embeddings that you get this way very clearly show the bias that is present in your data. And that's true for all deep learning methods, but Word2Vec was one of the first models where that was really shown very clearly. So here we see some word embeddings for different occupations, and we check whether they are more likely to be associated with the word he or the word she, with this male or female direction. And we clearly see that there is a very clear bias in some occupations being thought of as typically male and some occupations being thought of as typically female. In other words, there is a gender bias in our data, and that gender bias is reflected in our model. This isn't necessarily bad. For instance, if you want to study bias in the use of text, then this kind of model can actually help you do that. But practically, when you're using these kinds of models to build tools, you have to be very careful and very aware of these kinds of biases existing within the model, because they can do clear harm. Here is an example. In Google Translate, it used to be the case that if you fed Google Translate a gender-neutral sentence, like "my friend is a doctor," that doesn't indicate the gender of the friend in question. It might be that if you translate this sentence into a different language, it's not possible in that language to represent the sentence in a gender-neutral way. Here, for instance, there's a Spanish translation. It has two gendered words for friend, amigo, and amiga, and the translation model has to pick one of them. And here we see the bias appearing, that the model decides that because the friend is a doctor, the friend must therefore be male. Now, you may argue that these statistics are in a sense reflective of the biases that exist in society, so that it is indeed more likely that this sentence should be translated for a male. However, that doesn't mean that we're certain that the user wants the sentence translated in this way. And by reducing this uncertain prediction that we get from the data and from the model to a discrete and certain action, we run the risk not just of reproducing the bias in our data, but also amplifying it. And the solution here is very clear: to capture that uncertainty in the model, to be aware of it, and if you encounter a sentence like this, to offer the user both valid translations so that they can choose which one is applicable. So that's Word2Vec. It creates embedding vectors from words. You can download these standard embeddings from Google if you want to use them in your own projects. The training task is to predict context words. Given a word, predict which word is likely to occur in its context. In the embedding space that results from this training, distances and directions occasionally reflect semantic meanings as we understand them. And importantly for our current story, Word2Vec embeddings are a great starting point for deep learning projects on natural language. So if we're building a proper sequence-to-sequence model, what we can do is, instead of training an embedding layer like we saw in the first video, we simply import these Word2Vec embeddings and use that as our embedding layer. And then we can either use them as is, or we can use them to initialize our embeddings and actually fine-tune them to our current task. And the fact that this worked was quite an important breakthrough in natural language processing. Because what we see here is that if we have a difficult sequence-to-sequence task that requires a lot of annotated data, we can improve our performance on that task by pre-training a model in an unsupervised fashion. The Word2Vec can be trained in an unsupervised fashion. All we need is lots and lots of linguistic data, but we don't need any annotations. No humans need to go through the text and annotate it manually. If we're doing post tagging, we do need hand-annotated text, so we're always going to end up with a lot less data. And what this shows is that we can build an unsupervised model, train it on a large amount of data, and then use that model in a task that trains on small hand-annotated data. So this is pre-training or transfer learning, which we've seen already. But the breakthrough here is that it can be done using large unannotated data sets, which are cheap to acquire. And it's this principle that ELMo builds upon. And what ELMo adds to the picture of Word2Vec is contextual word embeddings. Word2Vec already gave us word embeddings, and in some sense it already looks at the context of a word to determine its meaning. But ultimately the word embedding that you get for a word here like dusted is always the same. So if we apply Word2Vec to these two sentences, the word dusted means exactly the same thing, or is represented in exactly the same way, where actually practically the meaning is exactly opposite in these two sentences. One is to add dust and one is to remove dust. In order to create a situation where you get word embeddings, word representations that capture this difference, what you need is contextual word embeddings. That is, you feed the entire sentence to a language model, and the model returns for you a word representation that depends not only on the word itself, but also on the context it occurs in. So that's the idea. we apply this pre-training principle. We pre-train on a large data set of unannotated text, but instead of producing word embeddings, we produce a sequence-to-sequence model that creates the word embeddings for us on the fly in context. So instead of transferring the embeddings, we are transferring the model. And there are a lot of models that did this. ELMo certainly didn't invent this principle, but ELMo was probably the first model that reached state-of-the-art performance on a large range of natural language processing benchmark tasks. And it led the way for a large number of models doing similar things like BERT and the GPT models, which we will discuss in Lecture 12. So let's look in detail at ELMo. It's a relatively straightforward sequence-to-sequence model, but it contains 3 points of interest that we will look at in more detail. The first is the way ELMo builds its non-contextual word representations that will feed into the rest of the model. This is not a simple embedding layer. Instead, ELMo uses character-based word representations. Here's broadly the way that looks. Our inputs are given to us as a sequence of words. We break these words up into their individual characters. The characters are fed to a character embedding layer. So for every character, we get an embedding vector. The sequence of these embedding vectors representing one word is fed to a set of convolutional neural networks, each with a different kernel width. These are combined and max pooled over the time dimension, and this resulting representation of the word is fed through 2 linear layers, each with a highway connection, which is a bit like a residual connection but parameterized. And from this we get a word representation. Now the benefit of this is that our word representations are character aware, so that if we see a new word that we haven't seen before, and in realistic natural language settings, this is a very important property, because a lot of the text that you're going to encounter may be misspelled. So for instance, if you misspell the word accommodations, it will still, in terms of its characters, look a lot like the correctly spelled word accommodations. So the embeddings will still be close together. So this gives us our non-contextual word representations. These are then fed into a sequence-to-sequence model, which brings us to probably the main innovation of ELMo, which is that it uses bidirectional LSTMs. So we built 2 multi-layer LSTMs, one that reads the sequence forward and one that reads the sequence backwards. And this, because LSTMs are causal models, this ameliorates the problem of only being able to look at the sequence in one direction. So both of these models produce contextual word embeddings, one based on the left context of the current word and one based on the right context of the current word. Now, the question is, how do we train this model? We can assume that we have a large amount of natural language, but no annotations. So putting these 2 together gives us a full model. We have a character-aware token representation. The tokens that result from this are fed to 2 multi-layer LSTMs. So now we need a way to train these LSTMs. And that is done by treating them as language models. We've seen the basic principle before. We called it autoregressive modeling then, but it's worth putting it into slightly more precise terms. A language model, in its most basic definition, is a probability model of language. It's a probability model that assigns a probability to a particular sequence of words or characters. We'll look at a word level sequence to explain the principle. So what we want is some probability distribution that will tell us how likely a sentence like this is to be encountered in a given setting. And the first thing we do is we break up the sentence into its tokens, in this case words, and we treat each of them as a random variable. So word 1 through word 6 are random variables, and these can each take on as their value one of the words in our vocabulary. And what we're looking for is the probability that the first random variable takes on the value congratulations, the second variable takes on the value you, and so on, until the 6th random variable, which should take on the value prize. And in shorthand, we will write that like this. Now, we don't usually have enough data to see even one complicated sentence multiple times. So what we need to do is break this probability value at the bottom up into multiple component parts based on conditional probability, which we can then estimate. And to do this, we will use this property of probability, which is simply, if you take the definition of conditional probability, you can rearrange it to get this. So the joint probability of x and y is equal to the probability of x conditioned on y times the probability of y. And we can apply this principle to decompose a probability for a sequence of random variables into a product of multiple conditional probabilities. That looks like this. We start with a sequence of random variables as before. We rearrange the random variables from last to first, which doesn't change the probability. And then we simply apply the rule that we saw in the previous slide first to the random variable w1, which looks like this. And we apply the same rule again to the random variable w2, which gives us this, and so on, until we've decomposed the whole joint probability into a sequence of conditional probabilities. Now we can do this in any order, but if we stick to the order in which the random variables are given, the natural sentence order, what we see is that we get a sequence of conditional probabilities where every word depends conditionally on the words that occur before it. So the probability that we're now looking to model is this. The probability of seeing a particular word, in this case price, given that we have seen the words before it, in this case, congratulations, you have won A. And if we can model this probability, then we can multiply all the probabilities that it gives us to give us a complete probability of the joint distribution. So in logarithmic terms, the log probability of a sentence is the sum over all log probabilities of the words in the sentence conditioned on all the words that came before it. And if you think back to what we talked about in the first slide, autoregressive modeling, you'll note that if we train a sequence-to-sequence model like this, we feed it with a particular input and we train it to predict the next word at every time step by giving it as a target value the input shifted 1 unit to the left. If we train our neural network like this, and we have an output layer over the vocabulary that is softmaxed so that it gives us probabilities over the vocabulary, we can interpret every single probability vector that this output gives us as the probability that we'll see a word given that we've seen the words that come before us. So the vector indicated here gives us the probability of seeing the word on, given that we've seen before it the words the, cat, and sat in that order. So to summarize, if we train a sequence-to-sequence model autoregressively with a softmax output layer, what we get is a conditional language model. Now this might just seem like a fairly simple statistical model that would be easy to train, but it actually turns out that if you look at what a perfect language model needs to be able to do, it captures not just syntax, not just grammar, but also semantics. For instance, if we see the sentence, the man fell out of the, there are different ways of completing this. And even a very simple language model can tell us that cycling does not fit grammatically, so it should get a very low probability. But it requires quite a sophisticated language model to choose between the options window, aquarium, and pool. They all fit grammatically. They're all nouns, and this sentence is completed by inserting a noun phrase. So a language model needs to have a certain kind of grasp of semantics and common sense in order to know that a window is much easier to fall out than an aquarium, and it's much more likely that people fall out of windows than out of aquarium. And if it's a particularly sophisticated language model, then it can even tell you that a person is more likely to fall out of an aquarium than out of a pool, even though both are so unlikely that these things have never been mentioned before in the corpus, that the model has never seen something like this described in the data set. If it contains a certain amount of common sense and knowledge about the world, then it can reason that at least an aquarium is something you could technically fall out of, whereas most pools it's actually impossible to fall out of because they are embedded in the ground. So all of this is just to say that a language model as a task, getting it absolutely right, is what we call AI complete. You need a complete understanding of the world and a complete intelligence in order to model the language completions correctly. This isn't practically true, but there are a lot of models these days that are coming pretty close to this sort of thing. So, putting all of that together, this is what the Alma model looks like. We are given a set of inputs as words. These are broken up into characters and fed to a CNN embedding layer, which gives us non-contextual vector representations of these words. These are fed to two separate LSTM language models, one which reads the sentence forwards and one which reads the sentence backwards. And both of these are trained separately as language models. How do we then take the resulting model and do fine-tuning? we take a weighted mixture of all the word embeddings produced in this ELMo model. So the ELMo model produces first non-contextual word embeddings, which we've called H init. For every word k in our sequence, we get a non-contextual word embedding hk init. And then for every layer in this forward LSTM, we get a contextual word embedding. And for every layer in our backward model, we get a contextual word embedding. So the way ELMo now allows you to fine-tune this is by summing up all of these contextual and non-contextual word embeddings in a weighted sum where the weights are parameters specific to the fine-tuning task. So all the purple values in this formula are values that are learned specifically for the task we are fine-tuning for. And then the contextual word embeddings, EK, that follow out of this are fed to another sequence-to-sequence model that is designed specifically for the task. And we won't go into the details here, but the paper outlines a large number of tasks on which it evaluates the performance of ELMo, and for each task a very particular model is designed to solve that task. And these are the main results presented in the paper. So on the left we see a number of tasks. Like Squad, for instance, is a natural language answering task where a small snippet of Wikipedia text is given and then a question is asked in natural language about that snippet of text. And the rest of the tasks are similarly hand-annotated, manually curated natural language processing tasks. And the main result from the paper was, first, that if we start with a baseline and then give that baseline instead of randomly initialized basic embeddings, we give it the ELMo embeddings, the performance improves massively. And the second conclusion is that the performance improves so much that on each of these 6 tasks, the resulting performance is state-of-the-art, is better than the performance that was up till that point could be achieved. So that's ELMo. It's a system that does large unsupervised pre-training and that allows small-scaled supervised fine-tuning. It contains as its basic structure a bidirectional LSTM, but it does still require elaborate fine-tuning architecture. So the architectures that achieve this kind of state-of-the-art performance on all of these tasks are still quite elaborate LSTM structures. However, what we see later after ELMo with these successor models like BERT and GPT, that this pressure reduces. That the better the pre-training model becomes, the simpler we can make our fine-tuning architectures. To the point where, in most cases nowadays, we can simply add one fine-tuning layer on top of our pre-trained model, and that's enough already to give us a very good performance. And we'll look more into that in lecture 12 when we start investigating self-attention.